Okay guys, our last type of structure then that we're going to look at is the metallic structure. And we're going to look at metallic structures and how the structures of those metals affect the properties of a typical metal. So, first thing we need to work out about a metallic structure is it giant or is it simple? So, the good news is there is only one type of metallic structure that we need to, or that you need to concern yourself with, and it is the one that is on here now. And hopefully all of you are able to look at that and realise that this must be a giant structure. It's a huge ongoing network of these cations and delocalized electrons that we looked at whenever we looked at metallic bonding. So it's a massive structure, just like, and a very well arranged lattice, just like we had when we looked at our ionic structures or our giant ionic lattices in the 2 videos ago. So it is giant. Most of you, hopefully from there, would be able to predict that this is going to have very high melting and boiling points, because you have to overcome the bonds within this structure in order to melt it, to get these little ions that are in here, these little balls that we represented by, to get them to be free from each other and therefore as a liquid. So the majority of metals have got pretty high melting point. Not as high as diamond and graphite that we looked at in the covalent structures video, but nonetheless still pretty high. Okay. So, the high melting and boiling points because we have to break all the very strong bonds that are in this giant structure here. Now let's have a look at a metal's ability to conduct electricity. Okay, so this is a fairly typical diagram of a metal. Okay, we have our positive cations here. Okay, our positive ions, positive metallic ions, and we have then the sea of delocalized electrons around it. And remember, the attraction that holds a metal together, the glue if you like, or the bond, is the electrostatic attraction between the positive ion and the delocalized electron. Similar to ionic, except in ionic it's a positive ion to the negative ion. Here it's positive ion to negative electron. And in this instance the electrons are mobile and they are able to move really in all directions. Unlike ionic bonding, where the negative charges, the negative ions, were in fixed positions when it's in a solid form. So how does this affect the properties of this? Well, you should all know by now that the movement of charge, movement of electrons, is essentially electrical current, the flow of electricity. So if I was to try and force electrons in to this end of the metal, what they would simply do is, because of their negative charge, they would repel these electrons that are already here. And these electrons are mobile, remember, so they will move through the lattice, repelling electrons as they go along. And those electrons then would come out the other side of the metal. And because of the free delocalized sea of electrons that we have in our metal, and the ability of those electrons to move, that means that charge is able to flow through a metallic substance. So metals can conduct electricity. Likewise, they can conduct heat. If I was to heat this side, the electrons would start to move faster because I would be giving them more kinetic energy through the heating process. That energy would be passed on from electron to electron to electron, and that energy would be simply passed along. So if I started heating this side, the energy would be passed along as heat energy, and therefore metals can also conduct electricity. So let's have a look at some other properties of metals. Well, another property that you need to be aware of is the fact that metals are both malleable and ductile. This is a photograph, I'm not sure how well it's come up, of copper, but you can see it's a thin piece of copper sheeting here. Now, you could certainly not do that with an ionic structure because it would just be brittle and it would break, it would snap. But you can do it with metals, and that is all down to a certain property that the structure of the metal has. And if we go back to or if we have a look at this diagram, okay, what we can see is that metals, okay, are arranged in these layers. So what we've done is we've just sort of taken one layer off this diagram and we've just had a look at the individual cations and the electrons. Now, the good thing about metallic bonds is because the bond is mobile and the electrons are constantly moving throughout the structure anyway. So if you think about it, the metallic bond is constantly being made and broken all the time. If I hit this with a hammer or some sort of force, I will break the bonds, absolutely. And if I did that in a covalent or an ionic substance, the bonds would permanently remain broken. But because the bonds within this structure are essentially being made and broken all the time, if I hit it with a hammer, okay, well therefore what will happen is that the bonds will be broken, but when I stop hitting it, they can reform. So we have this very special bonding system within metallic substances due to the structure that allows these substances to be, and it's a new word to some of you, maybe not all of you, to be malleable. And that word malleable just simply means that it can be hammered into shape. Okay, so your car body, well, really if you think of any metallic structure, you will see where it has been hammered into shape. So the next property that we need to have a little look at then is the fact that metals are also ductile, and ductile means that they can be pulled or shaped into thin wires. And this is for the same reason essentially. If you look at this structure, it is in layers, very thin layers. Okay? Now if I was to apply a force in that direction and another force in that direction, what would happen is that layer would slide that way, those layers would slide that way, and if I do that, the layers will simply slide past each other. Again, this is because the bonds can be broken, and if I stop pulling it into wires, then the bonds can simply be reformed again. They will remake. If I did that with an ionic substance or a covalent substance, mostly the bonds would be broken, but they wouldn't be remade. So that means that they're ductile, and that's vitally important for making these things into wires for your kettle or your computer or your iPod charger or overhead power cables. All of those things require ductility of metals. Okay, so we've covered there, guys, various different properties of metals. We've covered their melting point, we've covered their malleability, we've covered ductility, and we've covered conductivity as well. And that pretty much is metals. Now we're going to have a look at another substance which metals are used to produce, and this is called an alloy. And an alloy is very simply a mixture of two or more elements. One of them must be a metal. So this is how an alloy might look, where we have the metal atoms, okay, and then we have these darker atoms which are put into the alloy, mixed in with the alloy. One you might hear of is stainless steel, okay, where you have steel, iron mixed with, for example, chromium to prevent rusting. You have other types of steel as well, titanium steel, very hard steel, whereby the iron is put in with titanium. And what happens simply is that this stops or slows down or prevents the layers that we had earlier sliding past each other, so it disrupts this structure. Okay, the other thing it can do is you can put in things which are unreactive, and that means that the metal, iron in the one particular instance, will not react as quickly and rust as quickly then with water and with oxygen in the surroundings. So that's what an alloy is, okay? It's a substance made by mixing two or more elements, but one of them, remember in your definition, must be a metal. Okay guys, so that is alloys and metallic structures and properties done.